In this lab, we're going to observe the exponential decay of a series RC circuit made out of this resistor and this unknown capacitor. When I say that capacitor is unknown, I'm really not kidding. If you look on the capacitor itself, there are some symbols printed, but I don't know how to interpret those weird symbols to tell me what the value of this capacitor is. I just found it in a box somewhere. However, in order to check whether we're doing this right, we are going to test our method first with this capacitor. This one has a mark on it that I do know how to interpret. It says 0.05 Z, and that means it's 0.05 microfarads, or 50 nanofarads. We also know the value of the resistor. The color code on it is brown, black, orange, reading from left to right. And then there's a gold that tells you the tolerance on it. So if you figure out those 3 digits using the color codes for a resistor, brown is 1, black is 0, orange is 3. So what that means is it's 10 times 10 to the third, or it's a 10K resistor. So that's your first piece of data in this lab. This resistor is 10 kiloohms, and this capacitor is supposed to be 0.05 microfarads. The premise of this lab is admittedly a little bit artificial. I probably could have found out somewhere how to interpret the numbers on that blue capacitor. Also, if you do have a really unknown capacitor, there are other ways to determine its capacitance. They're probably easier than what we're going to do. I'm going to show you one here. So on this multimeter, it has these scales marked F for farads. This thing claims to be 50 nanofarads, this green capacitor right here. So I'm going to put this on a 200 nanofarad scale. And then it has these holes here. So I'm going to stick the tails of the capacitor nice and deep in those holes to get a reading. And it tells me that it's 56 nanofarads, which is within about 10% of what we expected. So with the known capacitor combined with the known resistor, we can figure out what the RC time constant should be. I'd like you to go ahead and figure out that RC time constant, and also take 1 over that time and see what that would be in frequency units. So go ahead and pause the video for a second and do that calculation. Okay, so if you work that out, you should have gotten about 500 microseconds for the RC time constant, or about half a millisecond. And in frequency units, a period of half a millisecond would correspond to about 2 kilohertz. So that gives you some idea of the frequencies we're going to want to use. We're going to use this square wave generator to drive our series RC circuit. So it's going to just repeatedly kick the capacitor by charging it up, and then the capacitor will discharge itself through the resistor. And it'll do that over and over again. I've put it on 100 hertz right now, and that's chosen so it's considerably longer than the RC time constant. That gives us time to see a lot of the exponential decay until it's pretty much completely decayed. To see this RC time constant and decay, we're going to use this oscilloscope. And this is a nice modern digital oscilloscope. One of the really good features on these things that you should use is it has a default setup button, which I'm going to use. The idea there is that after it does the default setup, then you know that there's no weird thing that's been selected on this scope by the previous person using it that would persist after you turn it back on. So it gives you a known good state. So I'm now going to use the scope to see the signal from the function generator. Right now the leads are floating, so I just get some noise and nothing meaningful. If I go like that, I now read a 0 voltage difference between the 2 wires. I'm going to go ahead and plug the black cable into the black output on the function generator. That's important because on this BNC to banana plug converter, it's labeled here which side is the ground, and there's a little tab there, and that means that's the ground supplied by this metal housing on the connector. That has to be connected to something that's also grounded. Since this is grounded and this is also grounded, if I were to connect something like the red cable to there, I would essentially be shorting across the inputs to the scope. So I've plugged in both cables. The function generator is turned down to 0 now on that voltage. So I'm going to go ahead and turn up the voltage. And you can see a square wave there. I can adjust the time scale with this seconds per division knob. So if I want to see more than one cycle, I can go like that. Now I'm going to go ahead and build my actual circuit. I'm going to disconnect these banana plug cables here. And I'm not turning down the function generator yet, just to demonstrate that it is safe to go ahead and touch these conductors. If you look on the amplitude here, it was at 0.3 of a volt, which is not going to hurt me. I can also verify that on the scope. The volts per division on the scope were 1 volt. So these are small voltages, so I can touch these. I don't feel anything. I don't get shocked. However, in general, when you're working with AC like this, it's probably a better idea to turn down the function generator. This thing can actually put out pretty big voltages, so there's no point in leaving it on in between measurements. So I'm going to make a series circuit out of my resistor and my known capacitor. I'm going to use alligator clips only where I have to because they don't make very reliable connections. I'm going to use the shortest cables I have handy, even though they're still kind of long for the job. So there's a connection from the resistor to the capacitor. Then I'm going to go from the capacitor back to the function generator. And I'm going to have this third red wire to go from the resistor to the function generator. And now, because this blue wire is the one that I hooked to the black grounded output of the function generator, I'm going to be constrained. No matter what I try to do, I'm going to have to send that to the ground on the scope, which means that really right now I'm set up appropriately in order to measure the voltage difference across the capacitor, because I'm constrained to have one of my connections here on this blue wire. So I'm going to go ahead and do that. I'm going to go from the grounded input of the scope straight to the blue wire, which is also grounded. Then I'm going to go from the other input of the scope. Now it's floating and I'm picking up some noise on the oscilloscope. That's probably 60 Hertz AC from the room. And then I'm going to go to the other side of the capacitor. So the oscilloscope, which works as a voltmeter, is now reading the voltage across the capacitor. I don't actually have any voltage on the scope because the function generator is turned off right now. But I'm going to turn the amplitude back up. So now I get a trace on the scope. And it looks kind of funky because it's not triggering correctly. If I push trigger menu over here, the white highlighted blocks of text are too hard to see on this video because they're too bright, sorry. But right now it says mode auto. So now I'm going to change that to mode normal. which gives me more manual control over the triggering. And now what's happening here is it's triggering in the middle of the scope, which is what happens on a fancy modern digital scope like this by default. But sometimes it's triggering when the signal is coming up, and sometimes it's triggering on a downward slope. And that actually should not happen, because here this says slope rising. However, what's happening is I have enough noise on this signal so that the noise can sometimes cause the slope to be the opposite of what it should be. So I want to get rid of some of that noise. So I'm going to click on this acquire button, and right here where it says average, I'm going to click that. It turns on some averaging so that it averages over several traces on the scope. Right now it says averages 16, and so what that means is it'll take 16 traces, average them together. That tends to average out the noise and make it a cleaner signal. And you can see now that I'm getting nice clean triggering. I've moved the camera closer to the screen now and turned down the brightness so those small fonts are more legible. If you recall, before we kind of arbitrarily set the frequency of the square wave to 100 Hertz, just to make it long enough to see a lot of exponential decay, so that the exponential decay is just getting really close to zero with each cycle. So you can see that happening. Each of these exponentials tails off and really flattens out before the next half of the square wave comes along and kicks it in the opposite direction. We can also check that the period of that makes sense. So here you can see that the time base is set on 5 milliseconds per division. So that means each of these 1 centimeter squares, like from there to there, is 5 milliseconds. You can see that the period of this function is from there to there. That's 2 divisions, which is 10 milliseconds, and that's what we expect for a 100 Hertz period. So now we want to actually measure the RC time constant of this circuit, which is much shorter than the period of the sine wave generator. And the sine wave generator's data is not especially important. I'm just using it as an example of how you would measure times from this scope. Now I want to zoom in on the time scale to a more appropriate scale to measure the short time constant of the actual RC decay. So I'm going to use the seconds per division knob, which controls that. That's off screen. And I'm going to turn that clockwise, which zooms in. That weird behavior in between, I think, is some kind of funky interaction between the averaging and the trigger. But now on this scale, I have a nice zoomed in view horizontally of that RC time constant. If you look at the vertical scale, you can see that it's going from about +2 divisions to about -2 divisions, and that's because of the amplitude we set on the function generator. So because it's already centered on that scale, I think this line right here really is my baseline for the end of the exponential decay. So now I can think of this like a graph of e to the minus x, where this line is the x-axis, and that's the beginning of the graph. And the graph starts at 4 divisions, 4 of these 1 centimeter squares. And we want to know how long it takes to fall off from that value to 4 over e. So I worked out 4 over e on a calculator. It's very close to 1.5. It's actually 1.47. So for our purposes, I'm going to call it 1.5. So the RC time constant that we're observing here is the time that it takes to go from 4 divisions above the baseline down to 1.5. So if I go over to 1.5, that is right about there. And that's happening at that point right there. So to make this easier to measure, I'm going to use the horizontal position knob on the scope to scoot this over a little bit to the left. So now the beginning of the decay is lined up as well as I can do on one of these lines on the graph paper grid. So now if I locate the 1.5 division height again, y equals 1.5 right there, and that's right at that point, which is 1.6 divisions after the beginning of the decay. And I forgot to point out that that was on a time base of 250 microseconds. So our RC time constant was 1.6 divisions multiplied by 250 microseconds. But in any case, I wasn't really that satisfied with that measurement. Measuring 1.6 divisions is measuring a small thing. I'd like to measure a big thing for precision. So the scope is acting kind of weird when I try to zoom in some more on the time base. So right now I'm on 250 microseconds. I'm going to zoom in to 50 microseconds, which is really a more appropriate time base. And you can see now that it's acting flaky. I'm no longer getting clean triggering. And I think it's probably because of these little vertical spikes in there. So for some reason on this time base I'm getting some interference from somewhere, and it's triggering on that sometimes, so I don't get a clean trigger. I did find a way to get around that on this scope, which I'll show you now. So first I'm going to fiddle with the trigger level a little bit to try to get it to show the thing I want to see, which is that falling pulse. But then it's also still showing me the tail end of a rising exponential, which I want to get rid of. So there's a simple way of getting rid of that, which is there's a run stop button on this scope. So I hit run stop, and it randomly stops on whatever trace it was on. That was not the one I wanted, so I'll try it again. And there we go. The second time around, I randomly stopped on the one that I wanted to see. So that was a way to work around that interference on the scope. So now I'm still starting at 4 divisions above the baseline, and I still want to go to 1.5 divisions above the baseline. But now this is going to be a much better measurement. 1.5 divisions is happening almost exactly there at that line. So that's 1, 2, 3, 4, 5, 6, 7, 8.0 divisions. So 8.0 divisions times 50 microseconds. So summarizing our results with the known capacitor, that's what we had. And if you work those numbers out, it's not great agreement. It's about 20 or 30% off compared to the value printed on the capacitor and the value that we roughly confirmed on the meter. So most likely that's because there's stray resistance and stray capacitance in the circuit, such as the resistance and capacitance of the input of the scope. Now I'm ready to swap in the unknown capacitor here, and I've got the known capacitor there on the scope. I want you to think for a second about what we would expect to happen if we put in a different value of capacitor. So there are two possibilities. The unknown capacitor could be either a higher value or a lower value than the unknown. Let's say, for the sake of argument, that it's going to be a higher value. If it's a higher value, I want you to pause the video and think about how you would expect that trace to change for a higher value of capacitance. Okay, so now I'm going to go ahead and swap it in. So now it's an open circuit, so I'm just reading the voltage from the function generator with no capacitor. And I think you can tell now that the exponential decay is a lot faster, but the period of the signal hasn't changed because the period is just set by whatever we set on the function generator and has nothing to do with the RC time constant of the circuit. So the faster exponential decay, you should now be able to figure out whether that means the new capacitance is bigger than the old one or smaller than the old one. Now let's go ahead and take quantitative data. So now I've got my function generator's amplitude turned up a little bit to help me see things better. So it's a total height of 6 squares when the exponential decay starts out. And just like before with the known capacitance, I'm going to go ahead and zoom in on the time base. I'm probably going to have some of the same hassles with triggering. And that looks like a pretty good scale. And I'm going to use the same trick for getting rid of the unwanted rising pulse. And there we go. So I think you can go ahead and measure the data off the screen now. I should probably actually adjust this so that it's starting at a convenient spot. So I'll use the horizontal position knob again. Move the trace so that it starts right on one of the vertical lines, and see how lucky I get with freezing it. Got it the first time. So now you can go ahead and pause the video and take the data that you need in order to determine the RC time constant with the new unknown capacitor.